Welcome to part 15 of the CipherVibe Cloud Security Capabilities series. This episode explains API security, why it matters, how the capability works, which mistakes weaken it, and how to build it in a measurable way. API security protects the interfaces through which applications, partners, users, devices, and automated agents exchange data and invoke business operations. The most serious API failures often involve authorization and business logic rather than a simple missing patch. The key idea is that a security capability is more than a product feature or a collection of alerts. It combines people, process, technology, decision rights, evidence, and continuous improvement. We will examine its architecture, operating workflow, failure modes, defensive controls, implementation roadmap, and useful metrics. Coverage is not the same as effectiveness. A dashboard can show thousands of checks while the capability still fails because evidence is stale, ownership is missing, or remediation is never verified. The business outcome should be explicit. Teams need to know which loss scenarios the capability reduces, which systems are in scope, and which remaining risks require a conscious decision. To understand API security, start with its architecture and vocabulary. The capability should create a traceable chain from source evidence to a security decision and then to an accountable action. First, API discovery combines gateways, specifications, code, traffic, DNS, service meshes, cloud inventories, and external attack surface evidence. Second, authentication verifies identity, while authorization decides whether that identity may perform this action on this object under these conditions. Third, schema and input validation constrain structure, types, size, content, and unexpected fields before business logic executes. Fourth, runtime analytics identify shadow APIs, sensitive data movement, abuse patterns, credential attacks, and deviations from expected clients. These concepts need shared identity, timestamps, provenance, ownership, and access control. Every summarized risk should link back to its source evidence and disclose missing information. A sound architecture separates collection, normalization, analysis, policy, workflow, and presentation. Teams can then test freshness, identity resolution, policy results, owner routing, and closure independently. Design for degraded conditions. Providers impose rate limits, schemas change, credentials expire, and events arrive late. A professional capability reports uncertainty and health instead of presenting incomplete information as fact. Trust boundaries deserve equal attention. Identify where data crosses accounts, tenants, regions, vendors, privilege levels, and administrative domains, then apply authentication, authorization, validation, encryption, and audit controls at those boundaries. A useful operating model for API security follows a repeatable evidence lifecycle. First, inventory internal, external, partner, mobile, legacy, GraphQL, event-driven, and machine-to-machine APIs with owners and environments. Second, classify data and operations, define authentication and object-level authorization, and document trust boundaries. Third, test specifications, code, deployed endpoints, business flows, negative authorization cases, and abuse scenarios. Fourth, enforce gateways and service controls for identity, validation, quotas, rate limits, logging, and policy. Fifth, monitor runtime traffic, investigate anomalies, retire unused versions, and feed incidents back into design and testing. The workflow does not end when a ticket closes or an API returns success. Security closure requires fresh evidence showing that the risky condition is gone and does not immediately recur. Ownership should be established before urgent findings arrive using service catalogs, business applications, on-call schedules, and escalation paths. Prioritization should explain the influence of exploitation, reachability, privilege, data, business criticality, compensating controls, and confidence. Repeated findings should drive changes to secure templates, defaults, libraries, identity patterns, and architecture standards. Define escalation points for missing owners, disputed priority, failed changes, and evidence that suggests active compromise. Those conditions should move into incident or risk governance rather than remaining indefinitely in a routine queue. The fastest way to evaluate API security is to study how the capability can fail. First, valid user credentials can exploit broken object-level authorization to access another customer's records. Second, shadow and forgotten API versions remain exposed outside normal gateway and testing controls. Third, mass assignment allows clients to modify sensitive fields developers did not intend to expose. Fourth, rate limiting by address alone fails against distributed clients, authenticated abuse, and expensive business operations. Fifth, detailed errors and excessive responses reveal internal structure or sensitive data. These failures share a pattern. A local measure looks successful while the full outcome is weak. A connector, scanner, or repair can report success while coverage, exploitability, or recurrence remains unresolved. Measure whether the program improves important coverage, shortens exposure time, removes attack paths, and prevents recurrence, not how many alerts it produces. Exceptions need a reason, owner, compensating controls, approval, and expiry. Automation should reflect confidence, reversibility, blast radius, and business impact. Test both through controlled failure exercises. Correlate weaknesses instead of reviewing them separately. A moderate configuration issue, broad identity grant, exposed service, and sensitive data store may combine into a severe path even when no individual alert looks critical. A dependable API security program uses defense in depth. No single scanner, policy, gateway, or agent should be expected to carry the entire outcome. First, maintain authoritative specifications, ownership, version lifecycle, and deployment inventory. Second, centralize authentication, but enforce authorization at the resource and business operation layer. Third, use strict schemas, allow listed fields, size limits, safe parsing, output minimization, and consistent errors. Fourth, apply quotas and abuse controls using identity, operation cost, behavior, device, and business context. Fifth, log security-relevant decisions, protect tokens, test negative cases, and monitor sensitive data movement. Control design should include preventive, detective, responsive, and recovery layers. Together, they establish safe defaults, identify drift, govern containment, and restore service. Least privilege applies to connectors, agents, orchestration identities, data stores, and administrators. Scope, separate, monitor, rotate, and test their access. Every control needs an owner and test strategy. Validate it with representative assets, negative cases, simulated attacks, provider failures, and rollback exercises. Integrate controls with engineering through clear pull requests, owner routing, reusable fixes, documented standards, and fast feedback. Preserve an evidence trail from detection through decision, approval, change, and verification. That lineage supports investigations, audits, lessons learned, and fair performance measurement without forcing teams to reconstruct history from separate systems. A practical implementation roadmap for API security should build trust before scale. First, discover internet-facing and sensitive APIs and identify owners, data, and authentication methods. Second, prioritize object authorization, token handling, shadow endpoints, and high-impact business actions. Third, integrate specification checks, code analysis, and negative security tests into delivery pipelines. Fourth, add runtime discovery and abuse detection with privacy-aware traffic handling. Fifth, create version retirement, incident response, and partner access governance as the API estate grows. The roadmap is incremental because a focused production scope lets teams validate evidence, ownership, workflow, and control safety before scaling. Useful measures include owned API coverage, shadow API count, authorization test coverage, sensitive endpoint exposure age, and abuse detection response time. Give every metric a precise definition, data source, owner, and known limitation. Pair lagging indicators such as exposure age with leading indicators such as coverage, control health, exception expiry, and secure template adoption. Maturity means the organization can discover important risk, explain it, assign it, act safely, verify the result, and learn from recurrence. Review the roadmap quarterly. Changes in architecture, threat activity, regulation, business strategy, and provider services can alter both priorities and assumptions. Retire metrics and controls that no longer guide useful decisions. For more cybersecurity market intelligence, research, and educational briefings, visit CipherVibe.com. CipherVibe is operated by Cloudsectech LLC. This video is general education, not legal, compliance, financial, or incident response advice. Never access or test systems without explicit written authorization.